Okay, so today we're going to talk about subatomic particles. Now, you're used to talking about ones like electrons and protons and neutrons, but the ones we're going to talk about today are actually a little bit different than that. It's going to get pretty weird. I'm just going to give you a heads up right now. So here's today's plan. We got a very busy day ahead of us. I apologize in advance. You guys will already be able to tell by looking at the time that this is going to be one very beefy lesson. Maybe I'll be wrong, though, but I really doubt I am. We're going to learn about the fundamental subatomic particles that are smaller than protons, neutrons, and electrons today. So in order that we're going to go through this today is we're going to first start talking about something called cloud and bubble chambers, which are devices that detected these subatomic particles. Then we have to have a little discussion on matter and antimatter. Then we'll talk about particle accelerators like the Large Hadron Collider. You may have heard of that before. Then we'll talk about those subatomic particles. We'll talk about something called quarks. And then we'll finish off with something called the standard model of particle physics. There's not going to be a lot of calculations today. It's just going to be more or less me explaining a bunch of really abstract ideas. Let me just tell you right now, if you need to like pause the video several times and like literally go for a walk in the middle of this, I wouldn't blame you. Like this is going to be a pretty weird lesson, but I have some very good news for you at the end of this lesson today. So stay tuned for that. Here we go. Anyway, let's get rolling. Okay, first things first, a cloud chamber is a container of air saturated with water vapor through which charged particles are passed. The motion of the ions through the water or through the vapor triggers condensation along their path, similar to that of exhaust trails of an airplane in the sky. These vapor trails then mark the path of the particle. So in this picture here, it might be a little bit hard to see, but you can see all like these little like lines that kind of buzz around here. Those are basically the particles being emitted through radioactive decay of radioactive radon gas. So radon gas is going under certain kinds of radioactive decay. I think it's alpha decay. I could be mistaken on that one. You'll just have to wait and see on that one. But either way, though, there are particles that are being emitted from that. Could be alpha particles. Maybe it's beta negative particles. Maybe it's beta positive particles. Those are the antimatter ones. But either way, though, it's going under radioactive decay, and we can see through these lines that form as condensation in the cloud chamber. Now, a bubble chamber operates on a very similar principle. In 1952, the bubble chamber was invented. It contains liquefied gas. When charged particles move through the liquid at high speeds, they vaporize the liquefied gas, which causes it to boil and form bubbles along the particle's path. So again, anything that's got a charge to it is going to pretty much offer enough energy to heat it up to the point where it vaporizes, and it creates these really interesting lines. It looks like an Andy Warhol painting or something like that. I don't know. They're kind of interesting. So analyzing the tracks within these chambers is similar to the detection chamber in a mass spectrometer. Remember, a mass spectrometer isolated things based on isotopes. Okay, so in other words, based on how many neutrons, or really I should say nucleons, it had in it. A magnetic field is applied to the chamber, and photographs of the paths can be analyzed to determine the charge and mass of the particles. Because the particles need to be charged in order to be affected by the magnetic field, cloud and bubble chambers do not provide much information about neutral particles. So if there was something that was released that didn't actually have a charge to it, or at least had a net charge of 0, these cloud and bubble chambers aren't going to really work too well, at least for detecting, for instance, their mass, right? So yeah, anyway, the curved path, again, that you see, like those little swivelly circles that show up in this, that's because of deflection from a magnetic field. All right, so the cloud and bubble chamber helped prove that there were more particles than just the proton, neutron, and electron, which were at one time thought to be the only fundamental particles. As a matter of fact, you probably thought that yesterday. Aha! In 1932, a cloud chamber photograph earned an American physicist the Nobel Prize because it showed the existence of a positron, which is proof that antimatter existed. You don't have to analyze it too much, but you can see like there's that little curved line that comes off the horizontal line there. Just based on the behavior of that line and what it was doing within the bubble chamber, they were able to determine that that was antimatter that was actually colliding with regular matter and therefore extinguishing it altogether, which is pretty crazy for 1932. All right, so about matter and antimatter, one property of antimatter is that a collision between a particle and its antiparticle can annihilate both particles and produce 2 gamma particles, which are high energy photons, of course. So in other words, 2 gamma photons. Likewise, the collision of 2 gamma particles, so if you actually were able to somehow collide a gamma ray with another gamma ray and combine the energy together, it can actually materialize and create a particle as well as an antiparticle. Now, the very strange thing about our universe is there is a huge disparity between the amount of matter and antimatter that exists in the universe. Pretty much everything we see in the universe, even I'll go further than that, literally everything that you and I can see in the universe when you look up at the sky at night is matter, right? So you think with these properties in our universe that there'd be more balance between matter and antimatter, but that's not the case. But again, through these cloud and bubble chamber experiments, we have been able to prove that antimatter is indeed a thing. As much as it sounds like science fiction, it isn't. It's actually a real thing. Anyway, moving on. Particle accelerators. Particle accelerators accelerate protons to extremely fast speeds within a circular tube using magnetic fields. So in other words, it just gets a magnetic field to get a proton going real quick. The protons are then directed towards a target, and the collision causes the target to break into subatomic particles. Because again, these are colliding at pretty much the speed of light. And protons are not photons, so a proton going at the speed of light is actually pretty impressive. The proton must be accelerated to extremely high velocities in order to give them enough kinetic energy to overcome the strong nuclear force, which holds the nucleus together. So in other words, they're providing it with enough energy that it'll actually knock away the strong nuclear force, completely holding an atom together all as one. Now, the targets of early accelerators were heavier nuclei, which would simply split them into lighter elements, but newer accelerators are breaking apart protons, which requires more energy. So for instance, some of the experiments they're doing in these particle accelerators, and again, the particle accelerators are gigantic circular paths. Often the biggest one is many kilometers in diameter. But what's basically happening is if we were zoom in on just one cross section of one individual part of this, they're basically getting a proton, like a very, very, very tiny particle going at near the speed of light, and they're colliding it with another proton going at near the speed of light, which of course creates a net collision as if both of these things are going twice the speed of light, which is absolutely incredible, right? So when matter is colliding at these extremely high velocities, it really breaks down a lot of these fundamental forces that hold things together. And that's where these subatomic particles can be detected and analyzed, at least as far as I'm aware. This is extremely advanced physics. But anyway, moving on. So the Large Hadron Collider, or LHC, in Switzerland is 27 kilometers in circumference and provides enough energy to accelerate protons to a speed that is 0.999999991 times c. So in other words, just barely underneath the speed of light, because the speed of light would be 1 full c, right? So meaning the protons will complete their 27-kilometer loop in about 90 milliseconds. Speeds this great equate to energies of 7 trillion electron volts for each proton, meaning a head-on collision will be equivalent to 14 trillion electron volts. 7 trillion in one way, 7 trillion in another. Particle accelerators are used for scientific research, but are also useful for other applications such as industry, medicine, and chemical analysis. You might want to do some research as to how that's true. I will be totally open and upfront with you. I have no idea. This is a very, very mysterious, very fascinating device that exists, and an absolute marvel of human engineering achievement. But it is some incredibly advanced physics, right? And in case you can't tell from this picture, this is actually looking like what it looks like inside the particle accelerator. And you might have a hard time seeing based on whatever screen you're looking at right now. But this right here, this is a guy. There's like a human being standing there. So in other words, we'll assume maybe he's 6 feet tall. Look how big this thing is. And it's shooting an individual proton through here and colliding it with another individual proton. Absolutely incredible, the stuff that goes on in here. A lot of interesting things, but we don't have time to talk about it. Here's an overhead map. The Large Hadron Collider really is actually, I said it was in Switzerland. It's in both Switzerland and in France. It's kind of a shared project between the two. Now this map, of course, is in miles, but again, it's about 27 kilometers in a full circumference. But anyway, moving on. All right, here we go. Here's the weird part, okay? So just buckle up on this one, okay? Now, cloud chambers, bubble chambers, and particle accelerators have led to the discovery of over 300 subatomic particles after the discovery of numerous new subatomic particles. Famous physicist Wolfgang Pauli was quoted as saying, "Had I foreseen this, I would have gone into botany." So in other words, there are so many other things other than just protons, neutrons, and electrons that it is absolutely wild. And it blew away even the most advanced physicists here with just how complex reality really is. Now, most of these particles are highly unstable on their own and have lifetimes of less than a millionth of a second, which, needless to say, makes them extremely hard to detect. And not to mention, all of these are often much smaller than even just an individual electron, right? Which is even way smaller than a proton or a neutron. So this picture here shows some of the basic, excuse me, the basic subatomic particles, as well as some things called bosons, which are more of like force carriers. We'll get into this a little bit later, but it really breaks things down into some really odd categories. And again, I will make it a little more clear later on. But there's things called fermions, and then there's another category called bosons. And here are the dividing lines between them. And fermions can be broken down into quarks and something else called leptons. Quarks we'll get into in greater detail later in this lesson. The only lepton I'm sure you've ever really thought of too much is an electron. But again, there's also neutrinos, which we've talked about as well, which are in the same category as you can see as electrons. Bosons are force carriers. We'll get into that maybe a little bit later, probably actually at the very end of this lesson today. You won't need to know too much about them. The only boson that is very intuitive for us to understand is the photon, right? But there's several others. And again, these are just the basic fundamental ones. There's over 300 others that also exist. Anyway, moving on. Subatomic particles are complex and are classified in many ways. The most basic classification for subatomic particles is whether or not they interact with a strong nuclear force. Hadrons do interact and leptons do not. Okay, so a hadron is another classification. The easiest way of thinking of a hadron would be like a neutron or a proton, because again, they're in the nucleus, so they will interact with a strong nuclear force. Leptons, however, do not. That's why electrons, which are a type of lepton, told you today was going to get pretty weird. Electrons, which are a type of lepton, don't actually interact with that force. Although there are numerous types of each, the most common hadrons are protons, neutrons. There it is right there. And the most common leptons are electrons, like I already mentioned. Another classification for particles is their spin. Really, I should put like quotations on that. Fermions are the most common and include the basic particles, protons, neutrons, and electrons, while bosons include far more obscure subatomic particles. Again, like I mentioned, we're not going to talk about bosons too much. So here's a little chart that hopefully makes it a little simpler. I know this is just really bizarre. You will likely want to jot this chart down. I would highly advise pausing here. If you have a textbook, like if you're one of those who borrowed my textbook, page 843 has a more complete list on this one, but this is nice and simple. This is about all you really need to understand. There are a few other new terms that exist in this chart, as you can see as well. Fermions can be either hadrons or leptons. Remember, hadrons are things like protons and neutrons. Leptons are things like electrons. Hadrons are often called baryons. You may have heard the term baryonic matter. Baryon is basically a word that kind of means heavy, right? So the things that are a little heavier, they are hadrons, which is a type of fermion. Leptons, on the other hand, lepton kind of means low mass, which includes electrons. But then we have our bosons. Remember, bosons are the force carriers. They've also been referred to as being mesons, which are, again, a type of hadron. Holy smokes, this just gets bizarre. But they're like the middleweight particle. Meson, of course, this mes part means like middle, okay? You don't need to know that in great detail. We really should move on. All right, here's the real meat and potatoes of today, not in terms of difficulty, but in terms of importance, quarks. Now, quarks, I think we have actually mentioned before in the past year, just because they are the building blocks of protons and neutrons. There are 6 types of quarks. Although there are 6 types of quarks, nucleons are composed of first-generation quarks, for which there are only 2 types. There are the up quark and the down quark, okay? Now, quarks are odd in that they have fractional electric charges. In other words, as much as we know a proton has a positive 1 charge, or an electron has a negative 1 charge, and a neutron has 0 charge, quarks actually have a fraction of a charge, right? Yeah, so anyway, we'll get into that a little bit more here in a second. And they also come in 3 things that they call color charges. They're not actually colors, but you have to have all 3 colors to keep things balanced. There's blue, red, and green. We won't need to talk about that too much. Worry more about the charge, please. Now, protons and neutrons are composed of 3 of the first-generation quarks in colors that would create a neutral color. That's why you had to have all 3, because it kind of just balance out. It's kind of like when you combine the 3 primary colors, you make white light. It's kind of the same idea here. Even though these aren't actually colors, they just use color as a way of describing them, because we don't actually have a way with our human brains to comprehend what's going on with that aspect of a quark. Now, there's also anti-quarks, which have the opposite charge of their corresponding quark. Okay, talk about that in a little bit here too. this picture, I took it right out of your textbook, I think. Protons and neutrons, again, are made up of quarks. If you look at the proton, you can see it's made of 2 up quarks and 1 down quark. So we can actually say a proton is a UUD, 2 up quarks, 1 down quark. Each up quark has a charge of positive 2/3, and each down quark has a charge of negative 1/3. Okay? So if you do a little bit of math on this one, if you're adding up all the charges of all the quarks, 2/3 plus 2/3 is 4/3, and then 4/3 minus 1/3 is 3/3. And positive 3/3 is the same thing as positive 1, hence why a proton has a positive 1 charge. Now, a neutron is made up of the same building blocks as a proton, except instead of 2 up quarks, it has 2 down quarks. So it has 1 up quark, 2 down quarks. Up quark, again, has a positive 2/3 charge. Down quarks have a negative 1/3 charge. So in other words, you add it all together, you're going to find that the net charge on this one is 0/3, or in other words, just 0, as it should be for a neutron. Okay? If this is overwhelming to you right now, like seriously, pause the video and just like go for a walk or something like that. Like stare at the sky for a while or something like that. Because this is weird. This is really challenging our notions of what matter really is. Anyway, this would actually be a really good time to take a break from this video. I know I've linked to it on Google Classroom. If I can remember, I'll also link to it in the description on this video. This is a video that actually shows a pretty good representation of all the different quarks. Now, there are 6 different quarks that you can know, but really we only care about the up and down quark in Physics 30. But there's some other really cool ones. There's one called a strange quark, another one called a charm quark, and then another one called a top quark and a bottom quark. But again, those other ones you really don't need to know for Physics 30. It's just up quark and down quark. Those are the only ones you need to know, but this video is really interesting. Give it a watch if you can. It's only about 3 minutes long. So just to summarize quarks, the first generation quarks, again, are just the up quark and the down quark. Up quark has a symbol of a U, kind of like a stylized one if you can. Down quark's like a stylized D if you can do that. The up quark is positive 2/3 E. I always think of up as being, it's better. It's better to be up than down, right? So it's got to be a bigger number and it's got to be positive. Boom. That's how I always remembered which one was which. Down quark, it's not as good being down, so it's a smaller number, and it's negative. That's how I don't know. It just worked for me. Now, remember though, quarks can also have anti-charges. It doesn't look like, I don't know if you're seeing it on my end, but it doesn't look like the bar was drawn correctly. An anti-up quark really should be a U with a full bar on top of it like that. Mine looks like it's just like a little bar. I'm pretty sure you're probably seeing the same thing. And then same with the anti-down quark, it should be a full bar over it. So U with a bar over top of it, that's an anti-up quark. It has the same charge as an up quark, it's just make it negative, that's all. So negative 2/3, and anti-down is positive 1/3. We won't really need to use these too much. We'll just use the up quark and the down quark. But still nice to know that there are anti-quarks to make antimatter as well, like an anti-proton, for instance. All right, quarks. Quarks were first proposed in 1963, so this is some pretty new stuff, right? Like, so when my parents were born, quarks weren't even thought of. Like, that's like, it might not mean anything to you guys, but to me, like, it was like, whoa, holy smokes, this is like new information. Now, although they've never been observed directly, there is evidence for their existence. I think they even mentioned in the video, I can't quite remember, but quarks don't exist on their own. They have to be part of something else. So again, they haven't been observed directly, but there is evidence. In experiments similar to Rutherford's scattering experiment, physicists have observed that high-energy electrons bend differently as they pass around a proton. The scattering pattern suggests that the mass and charge, especially the charge of a proton, are not evenly distributed. Okay, so that's kind of telling us that there's something smaller than a proton that's making it up. It's believed that quarks cannot exist on their own as free quarks. The theory is that you'd have to put so much energy in pulling 2 quarks apart, you'd actually create a quark and anti-quark pair. There's some interesting explanations on it. It's kind of like, imagine, I remember I saw one video where it's like, imagine a quark is like a gummy worm. And it's like you pull the gummy worm on both ends, you're trying to split it apart. All you're going to end with is it's going to break and you're going to have 2 gummy worms in the end, right? So you're not going to really get anywhere. You're not going to be able to like pull it apart and have different things. I don't know. You'd have to see the video. That explanation sucked. But again, if you saw the video, it would make more sense. I think I think there's a channel, I think it's called Physics Girl, actually, something like that. It's a lady who puts them together. Anyway, I don't know. You can look it up if you can. All right, so just illustrating that electrons bending around protons idea. This is what they're noticing with an experiment similar to Rutherford's scattering experiment. Is if you send electrons near a proton, depending on what side of the proton it hits, it's going to bend differently. Now, usually we think if you just had a positive proton, and then you got your negative electron coming in here, that it's going to be attracted to it one way or another, right? Because opposites attract and all that, right? But notice on this side, there is a very strong attraction, hence why it bent so much. But on this side, it was like it was repelled, right? So that kind of tells you that one side of a proton has a strong positive charge, but another side of a proton actually has a negative charge. Yes, there is an overall net charge of a positive, but there is a positive side and a negative side to a proton. Very, very bizarre, right? So quarks are what we think are responsible for that. Now, beta decay with quarks is another thing we can do with this. Recall that in beta negative decay, a neutron transforms into a proton and emits an electron and an antineutrino. An electron, of course, in beta negative decay, they call that a beta negative particle, right? Same thing as an electron. Beta negative particle, same thing as an electron. And an antineutrino. Now, with the quark model, one of the down quarks simply changes to an up quark, which then releases a beta particle to conserve charge. A beta negative decay can then be written as, well, this, right? So what's happening is you're having a neutron. Okay, so a neutron is an up quark with two down quarks. That neutralizes it right there. And it's turning it into a proton because really one of your down quarks becomes an up quark. And then you got your beta negative particle just to save your charges and all that, right? So all the charges are still balanced, ideally at least, I think. Oh yeah, they are. So 0 and then 1 and -1. Yeah, it all balances out, right? So note the charges of up and down quarks, UDD. So in other words, neutron is neutral and UUD has a charge of +1. Yeah, so there you go. Again, charge has to be conserved. That is one of the fundamental laws. But anyway, let's move on. All right, similarly, a beta positive decay can be written as this. Remember, beta positive is where a proton is becoming a neutron. Now, in this case, the antiparticle is actually the beta positive particle. They wrote it as E with a plus. Really, I'd like to write it as B with a plus. But either way, though, it's a positron. It's the antimatter version of an electron. And again, charge is balanced here. You got positive and neutral equals positive, right, on both sides of this. And the neutrino that forms is just kind of a way of conserving your energy overall. But anyway, we don't have to understand that full process, but there we go. All right, so it's just showing the masses of these and expressing it in terms of, you can express it in terms of Einstein's mass energy equivalence. That, of course, is E equals mc squared. You don't need to know this too much. Just keep in mind that mass can be expressed using these numbers. They are on your formula sheet. Yeah, so just keep that in mind. If you ever see something that's like mega electron volts per c squared, that is just another way of saying mass, just in a very, very strange unit. Okay, anyway, moving on. All right, this is the last thing we're getting to today. I'm actually amazed. I'm like, pat myself on the back here. We're at 23 minutes. I thought this was gonna be like a 50-minute lesson today. I'm not gonna lie. So we've actually made pretty good time. I'm happy about that. Anyway, so the standard model was first proposed in 1978. Like, holy smokes, that's actually like getting close to, like, woo, that's like modern days almost. Maybe not to you, I don't know. Anyway, so 1978, and it's currently the accepted model for subatomic particles. It contains concepts that describe the nature of matter and the fundamental forces. A few of the main points are listed below. I'll just read these to you guys real quick. All matter is composed of either quarks or leptons. The first generation quarks make up protons and neutrons. First generation quarks, of course, are referring to, hold on, I'm just getting my pen here. They're referring to your up and your down quark. And your first generation leptons are your electrons and your neutrinos, okay? Matter particles are known as fermions, right? So all matter is made up of fermions. There are 12 fermions and they have antiparticles each, right? So in other words, there's also antimatter made of like antifermions. Now, mediating particles called bosons account for forces between particles. So if you've ever wondered before, when we talk about something like the electromagnetic force, you go, okay, well, the electromagnetic force is kind of just saying that, charges, like charges repel and, opposite charges attract, blah, blah, blah. It's like, well, yeah, but have you ever wondered why? Like, what is causing that to happen? Why is that an aspect of our universe? Or even think about like gravity. What's causing gravity to act on things? Or even also think, of course, of what's holding atoms together. Why is there a nuclear force? What is that force doing to hold things together? Really bizarre stuff, right? So now the bosons, like I said, they account for those forces. The photon, which we, of course, have talked about a million times here, that's actually the mediating particle, or in other words, the boson, for the electromagnetic force. So photons are the particle that's responsible for that, right? And we have noticed before through certain electromagnetic interactions that photons can be released when there's a motion or an acceleration of an electron, right? So of course a boson can appear in those situations. There are currently 5 known bosons. Bosons do not have anti-counterparts because they're not antimatter. They're a force particle in a way. Now the standard model can explain 3 of the fundamental forces. Of course, those 3 fundamental forces we're talking about are the strong nuclear force, the weak nuclear force, and the electromagnetic force. It cannot, however, account for gravity. So gravity is not something that we have been able to explain using this standard model quite yet. So for example, there's no proof of a mediating particle, a boson, for gravity, but they have proposed one. They call it a graviton, but there is no proof right now that a graviton is something that even exists. There might be, but we're not there yet. What physicists are trying to get to, and it's going to be quite the ordeal getting there, is something called a grand unified theory that ties together all concepts of matter and all concepts of forces into one nice solid package that explains a little bit of everything. Now, to kind of simplify this, simplify the standard model, we're going to bring back up that picture from a little earlier, this one right here. This picture really is showing what the standard model is all about. You have your fermions, which are the matter particles, which of course can be either quarks or they can be leptons. Your quarks make up your heavier matter. Your leptons are the ones that don't interact with a strong nuclear force. Now your bosons are the particles that are responsible for the forces. Photons, as we mentioned, are responsible for the electromagnetic force, right? Or at least they're the mediating particle. I really should stop saying they're responsible for it. That's not exactly the best way of putting it, but they're the mediating particle, the particle that kind of blends the concept of electromagnetism. The gluon is one that I always find easy to remember because it kind of sounds like glue, right? The gluon is responsible for your strong nuclear force, okay? So it's the glue that's holding your atoms together. The gluons are holding that. Now the Z boson and the W boson, I'm pretty certain that they're responsible for the weak nuclear force. Don't quote me on that, because I will be honest with you, I'm not 100% sure right now. I probably should have checked before I started filming this lesson, but you know what? I'm not there yet. Maybe you want to look up Z and W boson and find out for yourself what they do. But again, I'm pretty sure that those are the mediating particles for the forces between different molecules. Now this last one up here, and notice I even gave it like a different color altogether because it really is the strangest of them all, is something called the Higgs boson. Now what's phenomenal about the Higgs boson is it was actually just given enough evidence to be something that's even strongly considered in 2013. I remember I was like finishing up university. I was taking either a physics or an astronomy course when they actually discovered the Higgs boson. And it was quite a phenomenal discovery because the Higgs boson is without a doubt the most complex of all the bosons. And it might be something that actually leads us to start connecting this to all of the fundamental forces. The Higgs boson is incredibly complex to understand, and the evidence that they had to determine its existence was very, very challenging to even explain. So I'm not even going to bother trying, but if you're interested, you can look up the Higgs boson as well and try to find some meaning as to what that boson even does. But again, to make things a little simpler for us, I just want to remind you, basically the only things I need you to understand are the up and the down quark make up your protons and neutrons, okay? Your electron is not part of your quark matter. So in other words, electrons are not made up of quarks, but rather they're a different type of matter or a different type of fermion called a lepton. Now they're in good company. They're with all the neutrinos that we would have talked about before. And as it turns out, there are other kinds of neutrinos other than just the ones we've been talking about. But that's about it. Yeah, and you know what? I think I'll just kind of call it quits on that one right there. And we're done. So I made amazing time today, 29 minutes, which might not sound amazing, but I thought it was going to be way longer. For practice, I want you guys to finish up your atomic physics assignment. You can complete the whole thing now. It is due at the end of tomorrow, so you have today to work on it, as well as some time tomorrow. Of course, with how this lesson is planned, tomorrow will be our Zoom, because as of now, you should be watching this on a Thursday, unless you're watching it early or whatever, but whatever, it's no big deal. During our Zoom, we can spend a little bit of time you know, going over any of the questions you might still be stuck on. So of course, that'll be your chance to ask me any questions live, and I will help you out. And that's your last physics assignment. So then, of course, there's a subatomic particles worksheet. That's page 66 to 69. You can focus on that if you wish, but again, your assignment is your priority right now. And that good news I was alluding to half an hour ago when I started this lesson is this is it. That was the last new concept in all of high school physics. You're done, right? So in other words, from here on out, it's just review. And as of recording this, it's currently June 3rd that I'm recording this. We are now aware that there will not be a final assessment. So in other words, the last thing that we have to do at the end of next week is write our atomic physics exam. So from now until next week, and again, by next week, I do mean Thursday the, what is that? Thursday the 18th, I think, of June. Between now and then, we just have to practice, and then we'll write that unit exam on that Thursday the 18th. Anyway, as usual, guys, if you have any questions, please let me know. Polish off that assignment as soon as you can. The answer key should be posted in Google Classroom, I believe in week 11 is where I'm going to put it, unless I also put it in the assignment page. I haven't actually decided yet. Anyway, I'm going to stop yabbering on. Best of luck, guys. Contact me if you need.